What's up, everyone? Welcome back. Today's challenge comes from the German Math Olympiad. It's a beautiful geometry problem that has puzzled a lot of students. The trick isn't complicated calculations, it's spotting the right construction. Let's see if we can solve it together. Let's begin with the figure. We have triangle ABC. Point P lies on the base BC, dividing the base into two segments. Now let's look at the information we're given. Side AB has the same length as segment CP. For convenience, let's call that common length A. So AB equals A, and CP also equals A. We're also given three angles. Angle PAC is X, angle PCA is 2X, and angle PBA is 10x. Our goal is to find the value of x. At first glance, there doesn't seem to be enough information. So instead of trying to force a solution, we're going to create one. Here's the clever construction. From point P, draw a new segment to a point Q so that angle APQ is exactly x. This one extra line unlocks the entire puzzle. Now look at triangle APQ. Angle APQ is x, and angle PAQ is also x. Since two angles are equal, this triangle is isosceles. Therefore, AQ equals PQ. Now use the exterior angle theorem. The exterior angle at Q equals the sum of the two remote interior angles. So the exterior angle is 2x. Now turn your attention to triangle CPQ. Angle PCQ is already 2x, and we just found that angle PQC is also 2x. So this triangle is isosceles as well. That means CP equals PQ. But CP was given to be A. So PQ equals A. And since AQ equals PQ, we also have AQ equals A. Now we've shown that both AB and AQ have length A. Next, draw the segment BQ. Now, let's look at the large triangle ABC. The angle at B is 10x. The angle at C is 2x. So the angle at A must be 180 degrees minus 12x. Now, focus on triangle ABQ. We already know that AB equals AQ. So this triangle is also isosceles. Let's call each base angle theta. Adding the three angles gives 180 degrees minus 12x plus theta equals 180 degrees. Simplifying, 2 theta equals 12x. So theta equals 6x. That means the angle at B inside triangle ABQ is 6x. But the entire angle, PBA, is 10x. So the remaining angle between PB and QB must be 4x. Now look at triangle CPQ. Its two interior angles are both 2x. So the exterior angle at P is 4x. Finally, consider triangle BPQ. Angle PBQ is 4x. Angle BPQ is also 4x. So triangle BPQ is another isosceles triangle. Therefore, BQ equals PQ. But we already proved that PQ equals A. So, BQ also equals A. Now look back at triangle ABQ. AB equals A, AQ equals A, and BQ equals A. All three sides are equal. So triangle ABQ is equilateral. Every angle in an equilateral triangle measures 60 degrees. Earlier, we proved that each base angle of triangle ABQ is 6x. So, 6x equals 60 degrees. Divide both sides by 6, and we get x equals 10 degrees. One carefully chosen construction creates a chain of isosceles triangles, and that chain leads us all the way to an equilateral triangle. That's the hidden idea behind this beautiful Olympiad problem. Did you spot the construction before the proof began? Let me know in the comments. Thanks for watching, and I'll see you in the next video.